third group of elements periodic system: boron, aluminum, gallium, indium, thallium. Third group is the first group we are looking at that has p electrons, so it has full ns2 subshell and one electron at p shell. It's located to the right from second group, between second and fourth group of periodic system. As usual, first element of this group is significantly different from all others. Nevertheless, one property is common. Most stable oxidation number is 3. All of them form 3+ ions, well, with the exception of boron, where M3+ ion never exists in solution. So any numbers related to ionic radius of boron do not make much sense. Boron stays aside as the smallest. It has very high melting point, 2300 degrees Celsius, and boils at around 4000. Electronegativity of boron is similar to electronegativity of hydrogen. Most common compounds of boron in nature are oxygen-containing compounds, starting from well-known boric acid that exists in nature as so-called sessilite mineral. Boric acid easily decomposes to boric anhydride or boron oxide, which is the same. It has trigonal structure. All these molecules are flat, and they crystallize as beautiful hexagonal crystals by employing system of hydrogen bonds. You can see them here. This is very weak acid. In water, it does not dissociate. It takes one more water molecule to make tetrahydroxo borate ion, and of course proton sitting on water molecule. Even with this process, it is very weak, and pH of its solution never exceeds 5. Its sodium salt, named borax, is the most common mineral of boron. Its colorless crystals, color is always coming from impurities, that has characteristic anion that has 1, 2, 3, 4 boron atoms, system of 1, 2, 3, 4, 5 oxygen atoms bridging, and 4 hydroxyl groups. All this has charge of 2-, which is balanced by 2 sodium ions, and it crystallizes with 8 molecules of water. Borax is widely used as laundry detergent. It can react with hydrogen peroxide to make peroxo borax, which will be a very powerful agent for laundry. It is also starting material for most of boron-containing compounds. Production of boron usually starts with boron oxide that can react with many reducing agents. One of them can be a liquid magnesium to make solid boron and appropriate oxide. Now, all these methods will give you very impure boron because of metal boride impurity. So the next step would be to convert this boron into halogenide, tribromide for example, distill it, and then reduce it with hydrogen, receiving much more pure solid boron, which next can be purified by different other designs to achieve very high purity when necessary. Structure of crystalline borons can be different. There are plenty of allotropes, and they are not very simple. Boron does not make covalent compounds. This is not metal, so covalent structures are quite complex. Boron oxide can be reduced with carbon, but it does not make boron itself. It makes boron carbide, B4C. It's not stoichiometric compound, and carbon monoxide. This is one of hardest known materials, behind only cubic boron nitride and diamond, the hardest. The structure is very interesting. They are icosahedral units of boron, and then some of them contain carbon atom, and then they are carbon atoms and boron atoms connecting these units. It's kind of very complex and beautiful structure. There are several different boron carbides with slightly different composition. Boron oxide can react with ammonia gas at very high temperature, giving boron nitride. There are several polymorphs of boron nitride. One of them resembles carbon, graphite. Another resembles another carbon, diamond. It's a little surprise because boron has 3 electrons, nitrogen has 5. So boron nitride should have 8 electrons for 2 of them, exactly like for 2 atoms of carbon. Now, cubic modification of boron nitride that has structure like diamond has hardness very similar to diamond. The crystals can be colorless, with some very small impurities becoming pale colored. Most of them are used for cutting tools. Different from diamond, boron nitride is very easy to process, very easy to make powders, to manufacture powders. So this material has lots of advantages for making cutting tools, worms, and different type of ceramics. To make halogen-containing compounds, you can directly react boron with halogens. But most commonly, we again starting with boron oxide. Then when we are adding fluoride, calcium fluoride, and sulfuric acid, in fact, by this reaction, we are making hydrofluoric acid, which in turn reacts to make BF3 gas that runs away from reaction mixture, and then calcium sulfate solid. You remember it's poorly soluble solid remains, and some water retains as hydrate of sulfuric acid. Sulfuric acid loves water, so this molecule will not run away at this. BF3 molecule is flat triangle, but it easily reacts with any Lewis basis, like ether. So most commonly, it is stored as solution in ether, BF3, and then ether molecule. This compound is liquid and relatively stable. This is gas and very aggressive. Similarly, we can have reaction of boron oxide with carbon and chlorine to receive boron trichloride and carbon monoxide. The same reaction can be run for bromide, but most commonly it is run with boron proper, or in industry from boron carbide. Again, reaction with carbon and halogen. All halogenides of boron easily react with moisture or liquid water to give boric acid and HCl, HBr, HF, whatever acid we are using. Very interesting compounds are compounds of boron with hydrogen. BF3 trifluoride reacts with lithium hydride to give compound B2H6 instead of simple BH3. This compound doesn't have boron-boron bond. Instead, it has hydrogen bonds of such structure. So there is one common orbital that contains two boron atoms and one hydrogen. Hydrogen atoms are not located at the straight line, and this assembly is almost quadratic. There are plenty of compounds like that of different structure. They are cationic, anionic, with very complex and very interesting chemistry. All of these compounds are unstable even with traces of air. They react with oxygen violently, very high heat effect, making boron oxide and water. It can react with moisture to make boric acid and hydrogen, again very violently. B2H6 easily reacts with lithium hydride, additional portion, to make lithium borohydride, or with sodium hydride to make sodium borohydride. In lab, you can reverse this reaction and make B2H6 out of sodium borohydride. Boron reacts with many of metals to make borides of very complex structure. For example, with calcium, it makes CaB6 of such a a beautiful composition, with the magnesium Mg3b6 has boron as flat hexagon, and then you have magnesium ions above and below that. There are plenty of other known borides of different composition, and they have enormous number of variable industrial uses. At the end, I want to attract your attention to boron-silicon similarity. We often see this similarity at diagonal between second and third period of periodic table. Boron and silicon both form acidic oxides, B2O3 and SiO2, and they are oxides of very weak acids. Boron and silicon form many polymeric oxide structures in glasses. Boron and silicon form flammable gaseous hydrides. Transition metal silicides and borides are hard, solid refractory materials, often with no fixed composition.